Hello again, calculus friends. Let's continue our path to finding derivatives. We had just, in the last video, talked about how to take the derivatives of polynomial functions or power functions, where you have an x raised to a number. So like x to the fourth became 4x cubed. And that was one of those derivative rules that we said comes from that limit definition of the derivative and patterns evolving and then realizing, oh, well, yeah, this makes sense. Well, we can take the derivatives of other functions, some of these called transcendental functions, like fancy functions, like trigonometry and exponentials and logarithmic functions, and that's what we're going to talk about today. But instead of leading into the algebra behind why those rules work the way they do, I'm going to lead into the graphs. So, as you listen to this video, I need you to please don't just copy what I'm doing down. Pause the video when I tell you to and try to do this on your own, and then check back and make sure that you got the right things. That's important. I need you to engage in the material today so that you have an anchor and not just a rule. Okay? Okay. So we are going to do the derivatives of some other functions here, and what I've started with is the graph of sine x, y equals sine x. And one of the things that you need to know is that we do calculus in radians only. So when we have a trig function, you want to make sure that you're in radians, because derivatives work differently when you're in radians than they do when they're in degrees. If you want to know how they work in degrees, come and see me later. But for now, we are in radians. Got it? Good. Let's go. So here's the graph of y equals sine x. And the instructions I wrote on here are use the instantaneous rate of change of this graph at interesting points to plot the graph of f prime on the same set of axes. So what we want to do here is we want to figure out what our slopes are. And so I look at this thing, and one of the things that we may have already talked about is that when you have something that has a slope of 0, that means it's horizontal. When a graph has a slope of 0 and it's not a perfectly horizontal line, that usually happens when the graph has like a hill or a valley, also known as a relative minimum or a relative maximum, because what's happening there is the slope is going from being positive to negative, and in between the positives and negatives, you have a 0. All this to say that at this point on y equals sine x, the slope is 0, which means that I know pi over 2, 0 is a point on the derivative, because the slopes of the original are the y values of the derivative. All right, so I have a slope of 0 there. I have a slope of 0 there. Cool. Let's see. Let's find some other slopes. At y equals, at x and y equals 0, at this point right here, my slope looks like this. And so if I wanted to estimate what the slope of that tangent line is, so I could plot it on the derivative, I would say, let's see, y goes up by 1 when x goes up by, I don't know, what are we? 1, 2, like 2/3 of the way to pi over 2, so maybe at like pi over 3-ish. This is not going to be perfect, okay? I'm just estimating. So it looks like my slope is x goes up by pi over 3 and y goes up by 1. And so if I look at that, that's really 3 over pi, and 3 over pi is 1. So at the beginning of the graph, my slope is approximately 1. Okay, cool. And then right here at pi, I have the exact same slope as when I started, except it's going downward, so now my slope is negative 1. And then back here at 2 pi, I have another slope of 1. And if I connect these dots in a curvy fashion, that should look familiar. That's the graph of cosine x. The derivative of sine x is cosine x. That's the rule. Cool. All right, so if the derivative of sine is cosine, now let's talk about the derivative of cosine. All right, I'm going to do that in blue here. Well, I already know that this pink graph that I just drew is the cosine curve. So now I'm going to draw the derivative of that and say, all right, well, cosine has a hill right here at x equals 0, so my slope is 0. Cosine has a valley at pi, so my derivative there is pi, and a hill over there. And then cosine slope at pi over 2 is the same downward line we were talking about before. That had a slope of -1. And then my slope at pi over 2 is +1. Oops. And if I connect those dots, that looks like the sine curve, but upside down, which is true because the derivative of cosine is negative sine. Okay, and now you just need to know that. The derivative of sine is cosine. The derivative of cosine is negative sine. All right, what do we do with that? Well, we can do things like find the first derivative, but we can actually find higher order derivative, second derivative, third derivative, 80th derivative. So example 1 says, now that you know that the derivative of sine is cosine and the derivative of cosine is negative sine, find the second derivative of f of x equals 3 sine x, also known as f double prime of x. When you find higher order derivatives, you put extra apostrophes up there. So if f of x is 3 sine x, then f prime of x, well, let's see, the 3 is a lead coefficient. Coefficients just hang out and wait for everything else to happen. So the 3 stays. The derivative of sine x is cosine x. Okay, there's f prime. F double prime is the derivative of f prime. And the derivative of 3 cosine x, the 3 still stays, and the derivative of cosine is negative sine. So the second derivative of 3 sine x is negative 3 sine x. Okay, we'll talk about what second derivatives mean later. The next one says find the fourth derivative of cosine x, also known as g with a foreign parenthesis x. So here's what happens. The more derivatives we take, we don't want to just have to count apostrophes because that would be annoying. And so what we do instead of counting apostrophes is after you do 3 apostrophes, you just go to putting a number in parentheses. Why is it in parentheses? Because if we wrote it like this, that looks a lot like g to the 4th, and that's not what I mean. So the parentheses are the notation that got adopted to mean the 4th derivative of g. So let's see, g is cosine. So g is cosine. I should say cosine x. G prime is the derivative of cosine. Well, we said that's negative sine. G double prime of x is the derivative of negative sine, so the negative is going to stay, and then the derivative of sine is cosine. G triple prime, the third derivative, is the derivative of negative cosine. Well, the derivative of cosine is negative sine, so the derivative of negative cosine would be positive sine. And then the fourth derivative, the derivative of sine x, is cosine x. And hey, look at that. I'm back to the beginning. G of x is cosine x. The fourth derivative of cosine x is itself. It goes in a circle. So there you go. There's the derivative of sine and cosine. We'll get to the other ones later, all right, for your trig functions. Now let's talk about e and ln. So what if I wanted the derivative of e to the x? All right, so here's the graph of e to the x. It says on the same set of axes, sketch a graph of h prime. So h of x is e to the x, sketch h prime. Now, if you think you can do this without me, feel free to pause the video and kind of come in here and draw some like tangent lines and plot the slope. So like at 1, if I sketch a tangent line, that looks like it kind of has a slope of 1. So I'm going to plot a 1. I'm going to keep coming in here and drawing in some tangent lines and estimating their slopes and plotting some points and seeing what happens. So if you think you can do this, pause this. Otherwise, I'm just going to keep rambling. So if I come back here to, let's say, -1, and I sketch in a slope, my slope at -1 looks like, I don't know, that one's kind of tough. to draw in there, except everything keeps scribbling. Kind of looks like I'm going like up 1 over 2-ish. So maybe have a slope of like a half. And then my slope at -2 is like even shallower than that. So maybe it's like over here. And then my slope at 1, let's see, here's my tangent line at 1. Looks like at 1 I'm going down 1, 2, 3.5, left 1.5. So I don't know, like maybe 2-ish or a little bit more. So if I connect the dots, wow, that looks a lot like what I started with. And guess what? It is. The derivative of e to the x is e to the x. The derivative of e to the x is itself. Okay? And that comes from the definition of e. 2.718, that number 2.718 has a lot of its roots in calculus and growth rates. And y equals e to the x is the only function whose first derivative is itself. And that's it. So the derivative of e to the x is e to the x. And then it says, if y equals e to the x, then what's the second derivative? Well, if the derivative of e to the x is e to the x, then the second derivative of e to the x is still e to the x. And there you go. Last one. So when we talk about y equals ln x, okay, y equals ln x, which is the inverse of y equals e to the x, if we do the same thing and we try to plot the derivative, okay, if you want, pause it, sketch in some slope lines. Otherwise, I'm just going to ramble a bit. So if I come here to 1 and I draw that in, it kind of looks like my slope at 1 is 1. Okay. Let's see, what's my slope at 2? So if I look at my slope at 2, I'm going up 1.5 over 1, 2, 3. So up a half over 3. It seems my slope is maybe like a half. Let's come over here. What's my slope doing here? That's like really steep, right? So my slope right here is like, I don't know. If I draw it purposefully like right at this spot, that slope is up 1, 2, 3, 4, 5 over 1. So that's going to be like way up here. So if I connect these dots, that's what the derivative of y equals ln x looks like. Well, what the heck is that? I'm going to tell you because this is not something you're going to come up with on your own. The derivative of y equals ln x is 1 over x. Okay? And that is just something that you need to memorize. The derivative of y equals ln x is 1 over x. 1 over x is a hyperbola that has two asymptotes. It has an asymptote along the y-axis, and it has an asymptote along the x-axis. So y equals ln x has a derivative of 1 over x, which can also be written as x to the -1, totally up to you. So part B says if y equals ln x, then what's the third derivative? Well, let's see. Y equals ln x d3y over dx3. Oh, I forgot to explain this notation. Those are your multiple derivatives. So the derivative of y is dy dx. And that's going to be 1 over x, which is x to the -1. Pardon me while I get a Kleenex. Okay. Now, if I want to take the next derivative, what we're actually doing is we're using this operator, d dx, which means take the derivative with respect to x. Okay. So if I use that operator, I want you to look at the notation on the left. So I'm doing d over dx, 2 dy dx, which means I have 2 d's and a y and 2 dx's. That's where that notation comes from. And if you're thinking, but you're not really multiplying those, you're right. It's just that we missed, what am I trying to say here? It's just that we matched, that's the word I wanted. It's just that we wanted to match the notation to what was actually happening in the like final notation for that derivative. All right. I over-explained that. Just deal with it. These little exponents aren't really exponents. They just tell you how many derivatives to take. So if y equals ln x, then the derivative of dy dx is d2y over dx squared, and the derivative of 1 over x is the same as the derivative of x to the negative 1, which is a power rule. Bring down the power, reduce it by 1. And then if I want the third derivative, I'm going to bring down the power, positive 2, reduce it by 1 again, 2x to the negative 3. And I do not care if you rewrite that as 2x to the negative 3 or 2 over x cubed, whatever you want. All right. I feel like this video is getting very long, so here's what I want to do next. I want you to try the next 3. Pause the video, do the next 3, and then I am going to give you the answers. All right? So pause it. Seriously. Seriously. No, for real, pause it. Here are the answers. The derivative of e to the x is e to the x. The derivative of 4 sine x is 4 cosine x. And the derivative of 2 ln x is 2 over x. If you want to make a tangent line, x, y, slope. If I want a tangent line to y equals 4 sine x at x equals pi over 6, x is pi over 6. Y is what I get when I plug pi over 6 into there. The sine of pi over 6 is the sine of 30. That's a half. 4 times a half is 2. The slope comes from the derivative. Well, if y is 4 sine x, then dy dx is 4 cosine x. I plug pi over 6 into there, and I get 4 times root 3 over 2, which is 2 root 3, making my tangent line y minus 2 equals 2 root 3 x minus pi over 6. And that's it. That's a tangent line. And last but not least, what is going on here? Mrs. Vibber, you said we'd never have to do those x plus h things. I didn't lie. You don't have to do the plus h things. You have to recognize it and reinterpret it. So when this says, find the limit as h approaches 0 of e to the 2 plus h minus e squared over h, I need your brain to remember that f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So your brain needs to look at that and go, wait a minute, I'm probably doing a derivative. Guess what? You are. Well, what's the 2 doing there? Well, the 2 is replacing the x, which means I'm taking a derivative and then I'm plugging in 2. What am I taking the derivative of? The thing that's being subtracted. So this limit actually translates to, hey, take the derivative of e to the x, then plug in 2. That's what that means. Well, I'll do that then. The derivative of e to the x is e to the x. Plugging in 2, I get e squared. And that's the answer. Okay, I have rambled. I am done. Everything's cool. I hope everybody had a wonderful day and is having a good day, and I will see you in math class. If I can turn off the video.